Welcome, curious minds, to another journey into the intricate dance of our universe. Tonight, we delve into a concept that reshapes how we view the very fabric of life on Earth: systems ecology. Imagine our planet not as a collection of separate pieces, but as a single, magnificent, living machine where every breath, every current, every economic decision is intricately linked. Prepare to unravel this interwoven tapestry, to find a profound understanding in the quiet contemplation of our world. As always, your engagement fuels these explorations, so please consider sharing your thoughts, leaving a like, or subscribing if you find solace and wonder in these deep dives. Now, let us begin. Welcome, dear listeners, to a journey into the intricate dance of life on our planet. Tonight, we delve into a fascinating perspective, one that sees Earth not just as a collection of separate parts, but as a grand, interconnected living machine. We're going to explore the world of systems ecology, a field that offers a truly holistic lens through which to understand the delicate balance and complex operations of the natural world. Imagine, for a moment, an intricate clockwork mechanism. Each gear, each spring, each tiny component has a role to play, influencing and being influenced by all the others. If one part falters, the entire system can be affected. This is, in essence, how systems ecology views our planet's ecosystems. It's an interdisciplinary field, drawing from various branches of science, but fundamentally, it applies the principles of general systems theory to the study of life's grand tapestry. At its very core, systems ecology embraces the idea that an ecosystem is not merely the sum of its parts. It is a complex system, constantly interacting and evolving, exhibiting what scientists call emergent properties. These are characteristics or behaviors that arise from the interactions of the individual components, but cannot be predicted or understood by looking at those components in isolation. Think of the swirling patterns of a flock of birds or the self-organizing structure of a termite mound. These are emergent properties of complex systems. Systems ecology concerns itself deeply with the myriad interactions and transactions that occur within and between biological and ecological systems. It asks fundamental questions about how energy flows, how matter cycles, and how information is exchanged across different scales of life, from the microscopic world of microbes to the vast expanses of our global climate. But perhaps what sets it apart, and what makes it so profoundly relevant to our modern existence, is its particular focus on how human interventions, our actions, our economies, and our societies influence the functioning of these magnificent natural systems. This field takes its inspiration, in part, from the rigorous methodologies developed in engineering and other disciplines for analyzing, characterizing, and even predicting the behavior of complex entities. It's about breaking down these intricate systems into understandable diagrams, identifying boundaries, and charting the flow of resources. As R.L. Kitching eloquently put it, systems ecology is the approach to the study of ecology of organisms using the techniques and philosophy of systems analysis. When a systems ecologist embarks on a study, one of the first crucial steps is to draw a diagram of the system of interest. These diagrams, with their solid lines indicating system boundaries, help us visualize the chosen components and their connections. We quickly realize that in ecology, we are almost exclusively dealing with open systems, systems that constantly exchange energy and matter with their surrounding environments. Unlike a perfectly sealed laboratory experiment, Earth's ecosystems are dynamic, breathing entities, always interacting with the world beyond their immediate borders. A central pillar of this mode of scientific inquiry is the general application of the principles of energetics to all systems, at any scale. The flow of energy is the lifeblood of every ecosystem, from the smallest bacterium to the largest whale. Perhaps the most notable proponent of this energetic view, often considered the father of ecosystems ecology, was Howard T. Odum. He envisioned these energetic principles as fundamental ecosystem laws, allowing systems ecologists to draw powerful analogies across different scales. He even developed an energy systems language to visualize these flows and interactions in his system diagrams. One particularly profound principle within this framework is the principle of maximum power efficiency. This concept suggests that the most evolutionarily advantageous system function occurs when the environmental load, or the demands placed upon the system, matches its internal resistance. When this balance is achieved, the system operates at its most sustainable and resilient state. The further a system deviates from this ideal match, the further it drifts from a sustainable equilibrium. This means that a key task for a systems ecologist, particularly in the realm of ecological engineering, becomes one of resistance and impedance matching, much like an electronic engineer fine-tuning a circuit. This intricate dance of energy and interaction is not confined to purely natural systems. Systems ecology takes an additional, crucial transdisciplinary step by integrating human economies into its consideration of ecological economic systems. This recognition stems from the undeniable truth that human activity, driven by economic forces, profoundly shapes and reshapes the planet's ecosystems. This leads us to closely related fields, which further illuminate the expansive reach of systems ecology. Consider Earth Systems Engineering and Management, or ESEM. This discipline is dedicated to analyzing, designing, engineering, and managing complex environmental systems. It's a truly multidisciplinary endeavor, weaving together anthropology, engineering, environmental science, ethics, and philosophy. At its heart, ESEM seeks to rationally design and manage coupled human-natural systems in a highly integrated and ethical fashion, acknowledging the deep and often turbulent connections between our societies and the natural world. Then there is ecological economics, a transdisciplinary field that explicitly addresses the dynamic and spatial interdependence between human economies and natural ecosystems. It's a fusion of insights from both the natural and social sciences, driven by a critical perspective on the assumptions of traditional environmental and resource economics. Ecological economists recognize that our economic models often fail to account for the fundamental limits and crucial services provided by ecosystems, urging a more integrated approach. Ecological energetics focuses specifically on the quantitative study of energy flow through ecological systems. It aims to uncover the principles that govern how energy moves through different trophic levels, those energy-availing stages in ecological networks. Within systems ecology, these principles of ecosystem energy flows are seen as fundamental ecosystem laws, formally analogous to the broader principles of energetics. The ecological humanities offer another fascinating bridge, aiming to connect the sciences and the humanities and to integrate Western, Eastern, and indigenous ways of knowing nature. Like ecocentric political theory, this field is characterized by a connectivity ontology, a way of understanding the world that emphasizes the interconnectedness of all things and a deep commitment to two fundamental axioms: the necessity of submitting to ecological laws and the recognition that humanity is an integral part of a much larger living system. And of course, there is ecosystem ecology itself, the integrated study of both the living and non-living components of ecosystems and their interactions within that framework. This science delves into how ecosystems work, exploring the roles of chemicals, bedrock, soil, plants, and animals, and examining the physical and biological structures that define them. While much of systems ecology can be seen as a subset of ecosystem ecology, with its holistic approach, systems ecology distinguishes itself by more actively considering external influences, such as economics, which often fall outside the traditional bounds of ecosystem ecology. Ecosystem ecology is the scientific study of ecosystems. Systems ecology is a particular approach, a specific lens through which to view these complex and fascinating systems and the phenomena that interact with them. Finally, we have industrial ecology, a field that shifts our perspective on industrial processes. Instead of seeing them as linear, open-loop systems where resources flow in and waste flows out. Industrial ecology envisions a closed-loop system. Here, waste products from one process become valuable inputs for another, mimicking the cyclical nature of natural ecosystems and striving for greater efficiency and sustainability. From these perspectives, it becomes clear that systems ecology is not just a branch of science. It's a way of thinking, a philosophy that urges us to see the world as an integrated, dynamic whole. It calls upon us to recognize the profound interconnectedness of all life and to understand that our actions, no matter how localized they may seem, ripple outward through the intricate web of existence. As we continue to navigate the challenges of our time, from climate change to biodiversity loss, the insights offered by systems ecology become increasingly vital. It empowers us to move beyond fragmented understanding and towards a more holistic and ultimately more sustainable relationship with our living planet. And in the quiet moments of contemplation, it allows us to marvel at the sheer genius of Earth's grand, living machine. Our journey into the intricate dance of Earth's living systems would be incomplete without delving into the profound insights of one of its most visionary architects, Howard T. Odum. If systems ecology views the world as a grand, interconnected machine, then Odum provided us with the blueprints and the underlying energetic laws that govern its every hum and whir. He is, for many, the very father of ecosystem ecology, a figure whose ideas continue to resonate and shape our understanding of the planet. Imagine, if you will, the entire universe, from the smallest microbe to the most colossal galaxy, as a ceaseless flow of energy. For Odum, this wasn't merely a poetic metaphor. It was the fundamental truth, the bedrock upon which all of life, all of existence, is built. He saw that the principles of energetics, those universal laws of energy flow and transformation that govern the very fabric of physics, are not confined to the sterile laboratories of thermodynamics. No, for Odum, these principles are the ecosystem principles, the driving force behind every rustle of leaves, every predator's hunt, every pulse of human civilization. Odum's genius lay in his ability to see formal analogies across vastly different systems, to recognize that the same energetic principles could be at play, whether we were examining a single cell, a vast forest, or indeed the entire global economy. He provided us with a powerful lens through which to view the world, one that emphasizes the relentless push and pull of energy, the continuous processes of creation and dissipation that define all living and non-living systems. To make these complex energetic flows comprehensible, Odum developed a unique and elegant tool, the energy systems language. Picture a series of symbols, a kind of hieroglyphics for energy that allowed him to diagram and chart the intricate pathways of energy from one component of a system to another. These wasn't just abstract drawing. These diagrams were living maps, revealing the sources, storages, flows, and transformations of energy within an ecosystem, within a society, within anything that breathes or moves or consumes. With this language, he could articulate the hidden grammar of life's energetic exchanges. Central to Odum's framework, and indeed to systems ecology as a whole, is a concept known as the principle of maximum power efficiency. This isn't just about efficiency in the traditional sense, but about the optimal flow of energy that allows a system to thrive and persist over time. Imagine a river flowing through a landscape. If the river flows too slowly, it becomes stagnant. If it flows too fast, it erodes its banks and dissipates its energy without sustaining life. There's a sweet spot, a balance, where the river's flow, its environmental load, matches the resistance of its channel, allowing it to do the most work to build the most robust ecosystem around it. For Odum, the same holds true for any ecological system. The most evolutionarily advantageous function, the most sustainable state, occurs when the environmental load, the demands placed upon the system, perfectly matches its internal resistance, its capacity to process and transform energy. The further a system deviates from this ideal match, the more it struggles, the less sustainable it becomes. It's a profound idea, suggesting that resilience and longevity are not simply about having abundant resources, but about the harmonious interplay between what a system is given and what it can effectively utilize. This principle extends far beyond the natural world. Consider human societies and economies. When our consumption, our environmental load, far exceeds the capacity of our planet's natural systems, its internal resistance, we create an imbalance that leads to unsustainable practices, to depletion, and ultimately to breakdown. Conversely, if we underutilize our potential, if our societal structures stifle innovation and efficient energy use, we also fail to achieve our maximum power. For the systems ecologist, then, the task becomes one of resistance and impedance matching, a phrase borrowed from electrical engineering, but applied with profound implications to the living world. Just as an electronic engineer fine-tunes components to ensure optimal energy transfer, so too does the systems ecologist seek to understand and, where possible, to adjust the flows and resistances within ecological and human systems to achieve a sustainable steady state. It's about designing our interactions with the natural world in a way that allows both humanity and the planet to flourish, not in isolation, but as deeply intertwined components of a larger, living machine. This perspective, born from Odum's energetic worldview, is what elevates systems ecology beyond a mere description of ecosystems. It provides a framework for active engagement, for ecological engineering, for guiding our collective actions toward a more sustainable future. It demands that we look at the world not as a collection of separate parts, but as a grand, integrated whole, constantly exchanging energy, constantly striving for a dynamic balance. The implications of this energetic lens ripple outward, connecting to several closely related fields, each building upon or refining the insights of systems ecology. One such field is Earth Systems Engineering and Management, or ESEM. This discipline is about intentionally designing and managing the complex interplay between human and natural systems. It brings together a vast array of subjects, from engineering to ethics, anthropology to environmental science, all with the goal of rationally shaping our interactions with the planet in an integrated and ethical manner. ESEM, in essence, takes Odum's principles of energetic matching and applies them to the grandest scale of all, our stewardship of the entire Earth system. Then there is ecological economics, a truly transdisciplinary field that explicitly addresses the dynamic and spatial interdependence between human economies and natural ecosystems. It's a field born out of a critical look at traditional economics, which often treats the environment as an external factor, a boundless resource, or a convenient waste sink. Ecological economics, by contrast, recognizes that our economies are not separate from nature, but are embedded within it, entirely dependent on its energy flows and material cycles. It brings together ecologists and economists, bridging the perceived divide between the natural and social sciences, recognizing that the health of our planet and the prosperity of our societies are inextricably linked. It is, in many ways, an extension of Odum's vision, applying the energetic accounting to the flow of goods, services, and wealth, not just through ecological webs, but through human communities. Another vital connection is found in ecological energetics itself, the quantitative study of energy flow through ecological systems. This field seeks to uncover the fundamental principles that govern how energy moves up through trophic levels, from producers to consumers, throughout the intricate networks of life. In systems ecology, these principles of energy flow are not just descriptions. They're considered the very ecosystem laws, formally analogous to the laws of physics, guiding the behavior and structure of all living systems. It's about understanding the very metabolism of the planet, the energetic heartbeat that sustains all life. And finally, we find resonance in the ecological humanities, a field that aims to bridge the divides not just between the sciences and humanities, but also between Western, Eastern, and indigenous ways of understanding nature. It is characterized by a connectivity ontology, a deep belief that all things are fundamentally interconnected, and a commitment to two core axioms: that humanity must submit to ecological laws, and that we are an integral part of a larger living system. This perspective, while rooted in philosophical and cultural inquiry, finds common ground with the scientific rigor of systems ecology, both recognizing that the universe is a unified, interconnected whole, governed by fundamental principles that we ignore at our peril. The relationship between systems ecology and ecosystem ecology, while often intertwined, bears a subtle but important distinction. Ecosystem ecology is the broader scientific study of ecosystems, encompassing a vast array of methods and approaches. Systems ecology, however, is a particular approach to this study, one characterized by its holistic perspective, its emphasis on energy flows, and its application of general systems theory. While much of systems ecology can be considered a subset of ecosystem ecology, systems ecology actively reaches outward, embracing external influences like economics, human culture, and even philosophy, areas that often fall outside the traditional boundaries of ecosystem ecology. It is, in essence, a way of thinking, a grand vision of interconnectedness, constantly seeking the underlying patterns and energetic truths that bind the universe together. Howard T. Odum, through his pioneering work, provided us with a powerful framework to understand these truths. He taught us to see the world as a complex tapestry woven with threads of energy, a living machine constantly transforming, evolving, and striving for balance. His legacy reminds us that to truly comprehend the planet and our place within it, we must look beyond the individual components and embrace the intricate dance of energy that orchestrates the grand symphony of life. As we delve deeper into the intricate dance of existence, we cannot ignore the profound impact of humanity's hand. For too long, we have perceived ourselves as separate from the natural world, observers rather than participants. Yet, the truth, as revealed by the insights of systems ecology, paints a vastly different picture. Here, the boundaries between the natural and the human-made begin to blur, revealing an undeniable interconnectedness that shapes the very fabric of our shared reality. Systems ecology, with its holistic lens, compels us to recognize that the functioning of any ecosystem, from the smallest pond to the vast global climate, is not an isolated phenomenon. Instead, it is inextricably linked to the decisions we make, the economies we build, and the societies we construct. This is where the discipline takes an audacious, yet utterly essential, transdisciplinary leap. It integrates the often disparate realms of ecology and economics, recognizing that they are not merely adjacent fields, but deeply interwoven threads in the grand tapestry of Earth systems. Imagine, if you will, the bustling metropolis, a testament to human ingenuity and economic prowess. From the soaring skyscrapers to the intricate networks of transportation, it appears to be a world entirely of our own making. But look closer. The energy that fuels those buildings, the water that sustains its inhabitants, the materials that form its very structure, all are drawn from the natural world. And the waste generated, the emissions released, the land transformed, all ripple back into the natural world, impacting its delicate balance. This is the ecological economic system in action, a complex feedback loop where every human action has an ecological consequence, and every ecological change has economic ramifications. R.L. Kitching, a pioneer in this field, eloquently articulated the essence of systems ecology as an application of systems analysis to the study of organisms and their environments. He described the initial, crucial step in understanding any ecological system: drawing a diagram. This isn't merely a sketch. It's a conceptual map delineating the system's boundaries, identifying its components, and illustrating the flows of energy and matter within it. Most importantly, it highlights the connections, or lack thereof, across those boundaries. While an idealized, closed system exists in theory, the reality of ecological work, and indeed of life itself, is one of open systems, constantly interacting, exchanging, and adapting with their surrounding environments. Central to this mode of scientific inquiry is the pervasive application of the principles of energetics to all systems, regardless of their scale. We spoke earlier of Howard T. Odum, often hailed as the father of ecosystems ecology, and his profound insights into the universal language of energy. For Odum, the principles of energetics were not just abstract concepts. They were the fundamental laws governing the universe, manifest in every living system. This perspective allows us to observe an analogous functioning of these principles across vast differences in scale, from the metabolic processes within a single cell to the intricate energy transfers across an entire biome. Odum's ingenious energy systems language, with its evocative symbols and flowcharts, provided a powerful tool for visually representing these complex energetic pathways, making the invisible flows of power palpable and comprehensible. Among these energetic principles, the principle of maximum power efficiency holds a particularly central place in the analysis and synthesis of ecological systems. It suggests a fascinating equilibrium. The most evolutionarily advantageous and sustainable system function occurs when the environmental load, the demands placed upon the system, perfectly matches its internal resistance, its capacity to absorb and respond to those demands. Consider a river system. If the environmental load, say, a sudden influx of pollutants or an excessive rate of water extraction, exceeds the river's internal resistance, its natural purification capacity, or its flow regulation mechanisms, the system veers away from its sustainable steady state. The systems ecologist, much like an electronic engineer meticulously matching resistance and impedance in a circuit, endeavors to identify and address these imbalances in ecological systems. This isn't merely about observation, it's about active engagement in what we might call ecological engineering. It's about understanding how to restore harmony, how to design systems that are resilient, and how to guide human interventions in a way that minimizes disruption and maximizes long-term sustainability. It is a profound shift from a passive understanding of nature to an active, responsible stewardship. This interdisciplinary approach naturally leads us to closely related fields, each offering its own unique perspective on the grand challenge of harmonizing human activity with the natural world. Take Earth Systems Engineering and Management, or ESEM. This discipline is a comprehensive endeavor to analyze, design, engineer, and manage complex environmental systems. It's a truly expansive field, drawing from anthropology, engineering, environmental science, ethics, and even philosophy. At its core, ESEM is driven by the audacious ambition to rationally design and manage coupled human-natural systems in a highly integrated and ethical fashion. It's about consciously shaping our future, not just reacting to it. Then there's ecological economics, a truly transdisciplinary field that directly confronts the dynamic and spatial interdependence between human economies and natural ecosystems. Born out of a critical examination of traditional environmental and resource economics, ecological economics challenges the often narrow assumptions of mainstream economic thought. It brings together researchers from diverse backgrounds, bridging the historical chasm between the natural and social sciences, recognizing that the health of our economies is inseparable from the health of our planet. Ecological energetics focuses specifically on the quantitative study of energy flow through ecological systems. It seeks to uncover the fundamental principles that govern how energy moves through different trophic levels, the energy-availing stages of ecological networks. In systems ecology, these ecosystem laws, or principles of ecological energetics, are considered formally analogous to the broader principles of thermodynamics, underscoring the universal nature of energy's influence. And then we have the ecological humanities, a field that aims to bridge the divides not only between the sciences and humanities, but also between Western, Eastern, and indigenous ways of knowing nature. It embodies a connectivity ontology, a deep understanding that all things are interconnected, and a fundamental commitment to two core axioms: the necessity of submitting to ecological laws and the profound realization that humanity is an integral part of a much larger living system. Finally, ecosystem ecology, while closely related, offers a slightly different focus. It's the integrated study of both the living, biotic components and the non-living, abiotic components of ecosystems, and how they interact within their specific frameworks. This science meticulously examines how ecosystems function, relating this functionality to their constituent parts: chemicals, bedrock, soil, plants, and animals. While much of systems ecology can be considered a subset of ecosystem ecology, the crucial distinction lies in systems ecology's more active and explicit consideration of external influences, such as economics, that often fall outside the traditional boundaries of ecosystem ecology. Ecosystem ecology, in essence, is the scientific study of ecosystems, while systems ecology represents a particular approach to understanding ecological systems and the broader phenomena that interact with them, including, crucially, the pervasive hand of humanity. This interconnected perspective extends to fields like industrial ecology, which scrutinizes industrial processes. Traditionally viewed as linear, open-loop systems where resources become waste, industrial ecology advocates for a closed-loop approach, where waste from one process becomes a valuable input for another. It's a vision of industry mirroring nature's efficiency, a testament to the powerful lessons we can glean from a systems-level understanding. As we continue our journey, recognizing humanity's integral role within these vast, interconnected systems, we begin to shift our perspective from one of dominance to one of thoughtful participation. The call of systems ecology is not merely to understand, but to actively engage, to manage, and to design our shared future with an awareness of the profound and inescapable links between our actions and the pulse of the living world. The stage is set for a deeper exploration of how we can move beyond boundaries, bridging science and philosophy to foster a truly ecological way of thinking, ensuring a sustainable vibration for all life on Earth. We have journeyed through the intricate tapestry of systems ecology, from its fundamental principles to its profound implications for understanding our living world. We've explored how it views ecosystems as complex, emergent systems, and how the pioneering work of individuals like Howard T. Odum illuminated the energetic underpinnings of life itself. We even delved into the sometimes uncomfortable, yet undeniably crucial, intersection of human economics and the natural world, recognizing that our financial flows are inextricably linked to the flows of energy and matter in the biosphere. But the reach of systems ecology extends even further, pushing beyond the conventional boundaries of scientific inquiry to touch upon realms traditionally considered philosophical. It beckons us to consider the very nature of existence, our place within it, and the deep, often unseen, connections that bind us to everything around us. This transdisciplinary spirit, this willingness to bridge seemingly disparate fields, is one of the most compelling aspects of systems ecology. It recognizes that the grand challenges we face today, climate change, resource depletion, biodiversity loss, cannot be neatly compartmentalized into isolated scientific disciplines. They demand a holistic understanding, a synthesis of knowledge that transcends the familiar silos of academia. Consider Earth Systems Engineering and Management, or ESEM, a discipline that embodies this very synthesis. ESEM doesn't just study environmental systems. It actively seeks to analyze, design, engineer, and ultimately manage them. It's a pragmatic, solution-oriented field that draws from anthropology to understand human behavior, engineering to devise sustainable solutions, environmental science to grasp the intricacies of natural processes, and ethics and philosophy to ensure our interventions are both responsible and just. At its heart, ESM strives to rationally design and manage coupled human-natural systems in a highly integrated and ethical fashion. It's an ambitious endeavor, a testament to the idea that we can consciously shape our interaction with the planet, but only if we understand the profound interdependencies at play. Then there's ecological economics, a field born from a similar recognition of interconnectedness, yet with a particular focus on the dynamic and spatial relationships between human economies and natural ecosystems. It's a field that explicitly challenges the assumptions of traditional economics, which often treats the environment as an external factor, a mere source of resources, or a sink for waste. Ecological economics, by contrast, positions the economy firmly within the larger ecological system, acknowledging that economic activity is entirely dependent on and profoundly impacts the health and resilience of natural systems. It brings together economists and ecologists, social scientists and natural scientists, in a collaborative effort to understand and manage these critical interdependencies. At a more fundamental level, systems ecology is underpinned by the principles of ecological energetics, the quantitative study of how energy flows through ecological systems. It seeks to uncover the universal laws that govern these energy transfers, from the smallest microbe to the largest forest. In the systems ecology framework, these principles of energy flow are seen as analogous to the fundamental laws of thermodynamics, powerful, overarching rules that dictate how all systems, whether living or non-living, operate. This perspective allows systems ecologists to draw profound insights, to see patterns and principles functioning across vast differences in scale and complexity, from the microscopic dance of atoms to the cosmic ballet of galaxies. And finally, we encounter the ecological humanities, a field that perhaps most profoundly demonstrates the philosophical reach of systems thinking. The ecological humanities aim to bridge the often stark divides between the sciences and the humanities, and even between Western and indigenous ways of knowing nature. It is characterized by what is called a connectivity ontology, a way of understanding being that emphasizes the fundamental interconnectedness of all things. It challenges us to submit to ecological laws, not as external constraints, but as intrinsic aspects of our shared reality. It insists that humanity is not separate from nature, but an integral part of a larger, living system. This concept of humanity as part of a larger living system is a cornerstone of systems ecology and, indeed, of much ecological thought. It directly contrasts with an anthropocentric worldview, where humans are seen as dominant over and distinct from nature. Instead, it invites us to adopt a more ecocentric perspective, recognizing our embeddedness within and dependence upon the intricate web of life. The relationship between systems ecology and ecosystem ecology is a fascinating one, sometimes overlapping, sometimes distinct. Ecosystem ecology is the integrated study of biotic and abiotic components within an ecosystem framework, looking at how chemicals, bedrock, soil, plants, and animals interact to create a functional whole. Much of what systems ecology does can be seen as a subset of ecosystem ecology, particularly its focus on interactions and emergent properties. However, systems ecology often takes a more expansive view, actively considering external influences like human economics, which frequently fall outside the traditional bounds of ecosystem ecology. Ecosystem ecology describes the scientific study of ecosystems, while systems ecology represents a particular, holistic approach to studying these systems and the myriad phenomena that interact with them. In essence, systems ecology is not just a scientific discipline, it is a way of seeing the world. It encourages us to look beyond the individual components and to perceive the patterns, the flows, the relationships that give rise to the whole. It invites us to consider the deep interconnectedness of all things, from the smallest cell to the largest galaxy, from the pulse of a human heart to the rhythm of the tides. This perspective, this connectivity ontology, has profound implications not only for our scientific understanding, but also for our ethical and philosophical frameworks. If we truly are part of a larger living system, if our actions ripple through the intricate web of life, then our responsibilities extend far beyond our immediate surroundings. We are called to be stewards, not just of isolated natural resources, but of the entire Earth system. As we conclude our exploration of systems ecology, I invite you to carry this holistic lens with you. See the world not as a collection of separate parts, but as a grand, interconnected system, constantly in motion, constantly evolving. Recognize the elegance of energy flows, the resilience of emergent properties, and the undeniable impact of human interventions. For in understanding these profound connections, we begin to truly understand ourselves, our place in the universe, and the vital role we play in the ongoing story of life on Earth. The universe, in all its complexity, is a grand, unfolding narrative, and systems ecology offers us a powerful way to read its most captivating chapters. May your understanding deepen and your sense of wonder continue to grow. As our journey through the interconnected world of systems ecology comes to a close for tonight, I hope you carry with you a renewed sense of wonder for the vast connections that bind our planet. To truly grasp the pulse of Earth, we must embrace its complexity, its emergent properties, and its profound responses to every single action. If this exploration resonated with you, I encourage you to like, share, and subscribe to continue our shared quest for knowledge. What aspects of systems thinking captivated you most? And what cosmic or quantum mysteries would you like us to unravel next? Share your thoughts below. Until our next deep dive, keep observing, keep questioning, and keep vibing with science.